Hi, this is Alfozia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is inflection points. Curves have a variety of features that can be classified and categorized. One item pertaining to the curves that we consider is where the graph of a function is increasing or decreasing. Another feature pertains to something known as concavity. This can roughly be thought of as the direction of that a portion of the curve faces. More formally, concavity is nothing but the direction of the curvature. A portion of the curve is said to be concave up if it is shaped like the letter U. A portion of the curve is said to be concave down if it is shaped like something following U, inverted U. It is easy to remember what this looks like if we think about a cave opening either upwards or concave up or downwards for concave down. An inflection point is where the curve changes its concavity. In other words, it is a point where a curve goes from concave up to concave down or vice versa. This video is the continuation of the previous video of the topic local maximums and minimums. Inflection points are where the function changes its concavity. Since concave up corresponds to the positive second derivative and concave down corresponds to a negative second derivative. Then, when the function changes from concave up to concave down or vice versa, the second derivative must be equal to 0 at that point, this particular point. So, the second derivative must be equal to 0 to be an inflection point. So, you have to make sure that the concavity actually changes at that particular point. We can see few examples and learn how to find the inflection points. Let's do an example to see what really happens. So here is a function given f of x is equal to x cube. Let's find the inflection points. Okay, maybe as well let's find any local maximum or local minimum as well. So let's start with getting the first derivative. Hope you all are familiar with finding the first derivative and second derivative. Yeah, in case if you have any query about that topic, finding the derivative, you can refer to one of our previous video. So let me find first derivative and second derivative one by one. So derivative of x cube would be 3x square. Same way, let us find the second derivative. So derivative of x square is 2x multiplied by 3. So that will give you 6x. We are asked to find the inflection point. So set the second derivative equal to 0 and solve for x. So this is how we find the possible inflection points. We have set the second derivative equal to 0. Second derivative is nothing but 6x. So let's solve for x. Dividing both the sides by 6, we will get x is equal to 0 here. We can see that if there is an inflection point, it has to be at x is equal to 0. But how do we know for sure if x is equal to 0 is an inflection point? We have to make sure that the concavity actually changes. So to do this, we have to pick a number on either side of x is equal to 0 and check what the concavity is that at those locations. You can refer a previous video, local maximum and local minimum. So you'll get a better idea of finding those. As I told earlier, we are going to pick two numbers on either side of this point. First, I have picked a negative number, negative 1 on left side and positive 1 on right side. Let's use this x is equal to negative 1 and x is equal to 1 to check. At x is equal to negative 1, just replace this negative 1 in second derivative. So if you replace x by negative 1, we'll get negative 6. Now check for x is equal to 1. If we check x is equal to 1, we'll get a positive number. If the second derivative is a negative number, it means concave down. Am I right? If the second derivative is a positive number, which means the function is concave up at x is equal to 1. Thus, we can see that the function has different concavities on either side of x is equal to 0 and the inflection point is at x is equal to 0. Am I right? Because it changes its concavity. Please note that the inflection point is not necessarily where the function crosses the x-axis. This is just an example, but it is the point where the concavity actually changes. Hope you are clear with this example. If you draw a line like this, you can see that the concavity changes at the point x is equal to 0. You can also try finding local maximum and local minimum for the same example and let me know the answer that you're getting in the comment section. Okay, let us now move on to the next example. Here is the next example. Let's look at f of x is equal to x raised to 4. So we are supposed to find the inflection point. As I told earlier, we have to find the first derivative and second derivative. After that, set the second derivative equal to 0 and solve for x. This is the first derivative. This is the second derivative for this function. Let's set this to 0 and solve for x. Dividing both the sides by 12 and taking square root will get 0. Am I right? X is equal to f double dash of x is equal to 0. So we are getting x is equal to 0. Since the second derivative is equal to 0, the function is neither concave up nor concave down at this point x is equal to 0. It could still be a local maximum or a local minimum, and it could even be an inflection point. So let's see if it is an inflection point or not. For this, we need to verify the concavity is different on either side of x is equal to 0. So just plot this number on a number line and pick 2 points on either side of x is equal to 0. I'm picking the easiest number, -1 and 1. Just plug in these values in f double dash of x and check what value you're getting, positive or negative. If I replace x by -1, I'm getting positive 12. Let's see for x is equal to 1. I'm getting same value, positive, positive. So if the second derivative is positive, we'll get a concave up. Am I right? So x is equal to 0. There is no inflection point. Since the second derivative is positive on either side of x is equal to 0, then the concavity is up on both the sides, and x is equal to 0 is not an inflection point because the concavity does not change. No, it could still be a local maximum or a local minimum. For that, you can use any one of the three methods which I told you in my previous video. Shotgun method, first derivative test, second derivative test. You can pick the one that you're very comfortable with. Concave up looks like a cup and a concave down looks like a frown. Some functions like parabola only have one kind of concavity, but more interesting functions may have a mixture of two. The graph might be concave down in one interval and concave up in the next interval. Some functions even switch back and forth between concave up and concave down infinitely many times. Any point at which concavity changes from concave up to concave down or from concave down to concave up is called an inflection point for that function. And please consider this example. F of x is ax square plus bx plus c. So parabola of this type has no inflection point because its graph is always concave up or concave down. Am I right? Inflection points may be difficult to spot on the graph itself, so you must rely on the calculus to find them. Basically, we use second derivative as we saw in the previous examples. F double dash greater than 0 on an interval, then f is concave up on that interval. If f double dash, the second derivative of the function, is less than 0 on an interval, then f is a concave down on that interval. So all you have to see is at which point the second derivative of the function changes its sign from positive to negative or from negative to positive. At that point x is equal to c, then there is an inflection point located at that particular point x is equal to c on the graph. So in particular, c comma f of c is an inflection point for the function. So here is a good rule of thumb. You look for the possible inflection points by setting second derivative equal to 0. That's because the only way for x, the second derivative of f, the function, to change signs is to pass through the neutral territory of 0. So, you have to assume the change is continuous anyway. I'll just give you the summary of this video. An inflection point is a point on the graph of the function at which the concavity changes. You should know what the concavity means. And the points of inflection can occur where the second derivative is 0. In other words, solve f double dash equal to 0 to find the potential inflection points. Even if second derivative is equal to 0, you can't conclude that there is an inflection point at x is equal to c. First, you have to determine whether the concavity actually changes at that point. Hope you're clear with this video. In case if you have any query regarding this topic, kindly let me know. See you in the next video. Have a great time ahead.